Alright, so in today's video, we're going to look at evaluating limits graphically and from a table. So just to refresh your memory a little bit, a limit the big idea of a limit is asking what output value does a function approach as its input approaches a certain value. So basically what that's asking is, as my x goes to a certain number, what value is my function approaching? What y value am I going to get out? We are not concerned about what the actual y value is at that point. We're concerned about what the function is approaching, what it's getting closer and closer and closer to. So let's go ahead and take a look at some of these graphs. And for each of these graphs, we want to find out if, suppose the function being graphed is called f of x, we want to find what the limit as x approaches a of f of x equals. So we want to know what that is for each of these graphs. So for this graph right here, this is graph number 1. As x goes towards this a value from both sides, as x goes towards this a value, our function is going to dip down towards this point right here. Same thing on this guy, it's going to dip down. So in this case, the limit as x approaches a of f of x is just going to be the function value at that point, because as x goes towards this value, the function is just going to approach whatever value it outputs at x equals a. So this is going to equal f of a. So let's say if this was at like 3, for example, this would be 3. Now let's go ahead and look at this case. Now in this case, as the x values approach a, we're still going to sort of dip down to this this point. However, we see that the function is not defined there. However, don't let this fool you. The limit as x goes to a of f of x is still equal to, if this was 3, it's still equal to 3, even though the function is not defined there, because remember, we're not concerned about what the actual function value is at that point. All we're concerned about is what it's approaching. So this would still end up being 3. So in this case, there's a removable discontinuity here, and as x approaches that a value, it's still going to approach the same y value that it would be having if it was defined at that point. And okay, so let's go to case number 3. Now in this case, as the limit as x approaches a is different on both sides. If you approach a from the left side, your function is going to go up towards positive infinity. But as you approach a from the right side, your function is dipping down towards negative infinity. So in formal mathematical terms, what we say is the limit as x approaches a from the left of f of x equals infinity, and the limit as x approaches a from the right of f of x is negative infinity. However, because the left and right hand limits don't match, in math we say that the limit as x goes to a of f of x actually does not exist, because the left-hand side and the right-hand side don't seem to agree about what this function is approaching at x equals a. So whenever your left and right-hand limits don't actually equal each other, your limit as x approaches that value is not defined. It does not exist. All right, now let's go to our next case. Now in this case, as x approaches a, we have an interesting situation here. This is called a jump discontinuity. Basically what that means is there's like a skip in the function where it is defined there, but it's also like not continuous. It's broken up. So as x approaches a of this function, from the left side, we're approaching whatever this value is. Let's say this was 2, and let's say this was 3. From the left side, we're approaching 2. However, if we approach from the right side, we're actually approaching 3. So again, we have a situation where our left and right hand limits don't actually match up. So the limit as x approaches a from the left of f of x equals 2, but the limit as x approaches a from the right of f of x is 3. So these two, so the limit as x approaches a from the left of f of x does not equal the limit as x approaches a from the right of f of x. Therefore, we can say that the limit as x approaches a of f of x does not exist again. So as you can see from the left and right, we're getting two different limits. So the limit is not going to exist at this point. All right, on to our final case study. So in this case, if we approach a from the left-hand side, we're going to go up, 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 up towards positive infinity. And if we approach from the right-hand side, again, we're going to go up towards positive infinity. So in this case, the left and right-hand limits do end up matching up. So what we say is the limit as x approaches a of f of x equals infinity. Even though it equals infinity and it's not exactly a number, we still consider this to be sort of defined, like the limit still exists, but it's not existing in a traditional sense that it approaches a certain value. So the key thing to remember with limits is, one, if the limit as x approaches a of f of x exists, then you must have the limit as x approaches a from the left equaling the limit as x approaches a from the right. This must be true. Secondly, just because f of a is not defined doesn't necessarily mean that the limit as x approaches a of f of x is also not defined. For example, if you go back to this case study, here f of a is not defined because there's a hole there. There's a removable discontinuity. However, our limit is still defined because we're not concerned about what f is at that point. All we're concerned about is what we're approaching. So that's how to analyze limits graphically. Now we're going to take a look at how to analyze them from a table. So in this case, we're given two tables. In this, it's not labeled, but let this be f, let this be, or x, let this be f of x. So we're concerned about what is the limit as x approaches 4, oh, that looks like a 9, 4 of f of x, all right? So as we're approaching 4 from the left, meaning we're getting closer and closer to 4 from the left-hand side, so it's 3.9, 3.99, all this data here, you can see that we're going from 12.25, 12.01, 12.000001. So this seems to be pointing towards 12. So the limit as x approaches 4 from the left of f of x seems to be 12. Now let's take a look at the right-hand side. As we're approaching 4 from the right, so 4.1, 4.01, 4.001, which is all this data right here, we can see that we're getting 11.75, 11.99, 11.99999. So again, this is also approaching 12. As you can see here, both the left and right-hand limits do match up. So our limit as x approaches 4 of f of x is going to end up being 12 also. All right, now let's look at the second example. Here we're also given a table, and we're asked what is the limit as x approaches 2 of f of x. So again, we're going to analyze the left and right-hand sides. All our data that's less than 2 is going to be our left-hand limit. So 1.9, 1.99, 1.999, that's all going to be approaching 2 from the left-hand side. And as you can see, our data is showing 0.34483, 0.33445, 0.33344. So it looks like as we approach 2 from the left, we're getting 0.3333, like it would eliminate all the 4s and continue to be 0.3. So it seems as though the limit as x approaches 2 from the left of f of x is going to equal 0.3 recurring. And now let's look at the right-hand side. So on the right-hand side, we're going from 2.1, 2.01, 2.001, so we're getting closer and closer to 2, and our f of x values are going from 0.32258, 0.33223, 0.33322. So again, we're looking as if we're going to approach 0.3 recurring. So we say that the limit as x approaches 2 from the right of f of x is also going to be equal to 0.3 recurring, which means that the limit as x approaches 2 of f of x equals 0.3 recurring. If you know your fractions well, you know that this is equal to 1/3. So our limit as x approaches 2 of f of x is equal to 1/3. So just to sum up what we've done so far, we've learned that a limit only concerns what the y value is approaching as the x input approaches a certain value. We don't care about what the function actually is equal to at that point. All we care about is what it's getting closer and closer to. So you can have a few cases. You can have cases where everything is defined and everything is smooth, continuous, and easy. You can have cases where it's all smooth except at that point it's not defined, but again, we don't care about that. All we care about is what it's approaching. You can have asymptotic functions where on the left and right hand sides, they'd seem to disagree, so our limit ends up not existing. You can have jump discontinuities where your function is defined at that point, but there's a sort of jump and it's not continuous at that point, in which case, if the two left-hand, right-hand side limits don't end up matching up, your limit is not defined. And again, we can have other asymptotic functions where on the left and right-hand side, even though it reaches infinity or negative infinity, both sides end up matching up, so our limit does exist. And for tables, you just have to make sure that your y values from either side, your left and right hand sides, as they get closer and closer to whatever value you have here. So in this case, it will be x approaches 4, and it will be 12. And you have to make sure that the left and right hand side limits agree, and these values are getting closer and closer and approaching something. Then your limit is defined. And we're done.